Even the professor was asleep. Okay, today is minimum cuts. A problem very dear to me. You will remember that in the first couple of lectures we talked about a contraction-based algorithm, about a contraction-based algorithm for minimum cuts. So let me sort of refresh all of that, right? We're given a graph G, and I'm going to be looking at undirected graphs. You can talk about minimum cut problems with directed graphs, but they're different. The algorithms I'll be talking about today mostly don't work. And we'll be using our usual n vertices, m edges notation. A cut is a two-way partition of the vertices. And its value is the number or total weight of edges crossing the partition. All right. We may sometimes talk about unweighted graphs where you're just counting edges, or we might put weights on them and you add up the weights. Obviously, if you're not worried about runtimes and things or space, you can turn your rational weights into integers by multiplying out the denominators, and then you can treat the integer-weighted edges as just a lot of unit-weight edges and go back to the undirected case. But for performance, you generally want to work with weights if you have them. Traditionally, this problem was solved with max flow. Right? Because obviously the cut separates some pair of vertices, and we want to find the minimum cut of minimum value in this graph. Max flow techniques work because whatever the minimum cut is, it separates some vertex S from some vertex T, and so the minimum cut is also an ST minimum cut for appropriately chosen S and T, and that means that if you compute all the ST min cuts, one of them will be the min cut. There are n squared pairs. In an undirected graph especially, you don't need to look at all n squared pairs because the orientation doesn't matter. And so you just pick one specific vertex S and compute the ST min cut for every T, and one of these will be the minimum cut. Yes? Okay. And so you can use these max flow techniques. You can use n max flows. And that means that the runtime is something like order mn squared using traditional algorithms. There's been a lot of progress in max flow. Recently, a gigantic paper was published that achieved a near linear time algorithm for max flow, so that would improve this running time to order mn. The time for what used to be a single max flow. But in the early lectures, I also talked about a contraction-based approach, right? Find any non-min-cut edge and just contract it, right? This doesn't change the min-cut. Right? Contracting an edge destroys some of the cuts in the graph, but if it's not crossing the minimum cut, it doesn't destroy the minimum cut. So the minimum cut is still there, and it doesn't make any cuts smaller. So whatever was the min cut is still the min cut, and so you can recurse. Okay, and I mentioned that Nagamochi and Ibaraki developed this algorithm for finding a non-minimum cut edge in linear time. And so you can run their algorithm n times. Each of those runs will contract one edge and shrink the graph by one, and you'll end up with a graph that has two vertices. And in a 2-vertex graph, the minimum cut is obvious, right? Okay, so Nagamochi Ibaraki gave us this linear time contraction, which gave you the min cut in order mn time. But then we introduced this idea of just trying a random edge. Okay. And for talking about a random edge, to talk about trying a random edge, it's cleaner to assume that you're working with an unweighted graph, right? You pick an edge uniformly at random. Cut values are just the number of edges crossing the cut, and so forth, right? So what we said was, if you have a min cut of C, what this tells you is that the minimum degree is at least C, because a single vertex can be a cut, right? That vertex be on one side and everything else on the other gives you a cut whose value is equal to the degree. So every degree is a cut, so every degree has to be at least the minimum cut. This means that the number of edges is at least NC over 2, which means that your probability of picking a min cut edge is at most 2 over n. Right? This is all just reminding from week 1. All right? And so if we iterate this process, then the probability that we never pick a min cut edge is 1 minus 2 over, or at least 1 minus 2 over n times 1 minus 2 over n minus 1, and so on down to the final contraction when you have 3 vertices left, and there's a 2/3 chance that you'll pick a min cut edge. This can also be written as n minus 2 over n times n minus 3 over n minus 1 times n minus 4 over n minus 2, all the way down to 1 over 3. And what we noticed was that everything sort of nicely cancels out in this telescopes, so that all you're left with is a 1 over n over here and a 1 over n minus 1 over here, and a 2 and a 1 over here. So you end up with 2 over n times n minus 1, which just happens to be n choose 2 inverse, which is an interesting number. We'll come back to that. So this simple contraction algorithm has a roughly 1 in n squared chance of contracting the graph down to just being a single cut, which is the minimum cut of the original graph. Yeah? And we ran through all of that in the first lecture or second lecture. Any questions about it? Okay, so somebody did have a question about it, which was a very good question that I told them to wait a few weeks. Does anybody remember what the question was? You're not hanging on every word of your classmates? Yes?
Well, I remember it because I asked the question.
Good.
So, my question was, what if you stop selecting random edges at, after you're done with, say, n minus square root of n, or some much smaller value of n, and then just use the different algorithm that, will deterministically
Good.
use the correct.
Good. So we have these algorithms. We have this algorithm over here, which I will simplify to be an n cubed algorithm. I don't want to keep track of 2 separate parameters, right? If we look at sort of the source of trouble in the contraction algorithm, right? While the graph is big, our chances of making a mistake are small. It is only as the graph gets extremely small that this algorithm becomes unreliable, right? So you might try running this algorithm while the graph is big, and assuming that everything goes your way and you don't contract the minimum cut edge, you'll end up with a somewhat smaller graph. And now don't try to be randomized. Use use our deterministic algorithm so you don't have to worry about the unreliability when the graph is small. Yes? Okay. So, idea. Let's contract to some, say, S vertices. Then run our favorite, or just run our S cubed algorithm. Right? We can choose S however we like, but let's think about what we should do. Right? So we need to think about the runtime of this one iteration. Right? We talked about, you still have to implement the contractions. And, for most values of S, you're going to do most of the work of the contracting. Okay? So I'm just going to say that you are going to spend n squared work contracting your edges. Okay, it might be a little bit less, but it's certainly at most n squared. And then we run for S cubed time on the small graph. Yes? But what's the benefit? The benefit is in the probability of success. So how can we assess the probability of success if we contract to S vertices? Yes?
Like you only take this, the first n minus, n minus S terms of this product?
Exactly. So we're going to stop at 1 minus 2 over S or so, right? Right? There's somewhere in the middle, we have 1 minus 2 over S, 1 minus 2 over S, right? And we're just going to stop here instead of going all the way down. Okay? So what did that save us? Well, it saved us the terms over here, right? Which, if you think about it, are just telescope to 1 over S squared, right? So since the whole thing is 1 over n squared, and we've saved 1 over S squared, it means that our probability of success is S over n squared. Does everybody buy that? Okay. What do we how do we have to put these together? Well, we now have to, this is a small probability of success. We want a large probability of success. So what do we do? Yes. And how many times should we run this algorithm if we want a large probability of success? Exactly. So we are going to run, and I'm going to introduce some notation here because I really don't like writing all of the logs. Okay, so O tilde of f of n means order of f of n times some polylog in n. Okay? I'm interested in the degrees of the polynomials, and I'm not going to worry about the logs. I can assure you that there won't be too many logs. We're not going to end up with any sort of log to the 50th n type algorithms here. It just makes all of the notation cleaner. Okay, so if we're running it n over s squared times in a single iteration takes n squared over s cubed time, we now have a running time of n over s squared times n squared plus s squared. Yes? Sorry, s cubed. Okay. And so now we can go to work optimizing optimizing this algorithm. And I won't take us through all the steps. What I will note is that this n squared term doesn't really change whatever we do with s. So making s really small doesn't help us because we're still stuck with the n squared. Right? On the other hand, if we make s cubed bigger than n squared, well, this is outgrowing that, and so that's not a good idea either. So you can rapidly conclude that the way to optimize this is to set s cubed equal to n squared. Okay? So if I set s equal to n to the 2/3, then I get a runtime of n to the 2/3 on the outside times n squared on the inside, or n to the 8/3. Woohoo! Right? We just beat the n cubed of the deterministic algorithm. Okay? So we had a algorithm that was reliable but slow, and we incorporated it into our fast, unreliable algorithm and got a faster algorithm that is reliable but slow. This should give us pause. Now that we have a reliable n to the 8/3 algorithm, what should we do? Yes?
Why do we even bother using the deterministic algorithm? We could just always use our randomized algorithm.
Why?
But it's faster.
But it's not reliable.
But it's very fast.
Well, again, if we run our, that was the original design of the randomized algorithm, right? So we ran this algorithm, we had this algorithm that only took n squared time, but we had to run it n squared times, so it actually was an n to the 4th time algorithm. Right? Yes?
Now, you can iterate the improvement.
Yes, we can iterate the improvement. And this, I'm teaching it this way because this is exactly what I tried, like what I did. Okay, I've got this n to the 8/3 here, but that's better than n cubed, so why don't I just use that up here, right? So now we go n squared plus s to the 8/3 as our runtime if we stop at size s and switch to the n to the 8/3 algorithm. Yes? And then we still have we still need to do n over s squared iterations because we haven't changed the reliability of the algorithm at all, right? It still has an n over s squared chance of success. But now, same sort of balancing argument, we should set n squared equal s to the 8/3, which means that s is equal to n to the 3/4 instead of n to the 2/3, right? And if we plug in n to the 3/4 here, then what we have is n to the 1/2 times n squared, or n to the 5/2. Ooh, we got a faster algorithm. Okay. But now we can do this again, except I'm not going to because I don't want to use up all the boards, right? What's going on here? So if you try and sort of sketch out this recursive algorithm, right, what we're doing is we're starting with G, and we're doing a whole bunch of iterations where we take it down if we're using, say, the n to the 5/2 algorithm, right? We're going down to size n to the 3/4, right? And at that point, we're using the n to the 8/3 algorithm, which is also just running a whole bunch of contractions down to, it would be n to the 3/4 raised to the 2/3 power, right? Or down to square root of n, right? And then this is running a whole bunch of contractions down to 1, right? So if you look at this picture and don't worry about the exact numbers, it starts to tell you what's going on, right? That you're starting with your graph G, and you're doing some number of experiments that involve doing contractions and then recursing, right? And what we're doing as we sort of iterate this improvement is we're getting these better and better algorithms, which mean that it makes sense to stop the contractions sooner and sooner. right? In our first attempt, we were stopping the contractions at n to the 2/3. In our second attempt, we were stopping at n to the 3/4. You can imagine that if we do this again, we'll be stopping at n to the 4/5, and then n to the 5/6, and so forth. So we'll be stopping sooner and sooner before we then branch out into some other recursions. Okay? So if you noodle on this for a while, you can figure out that you should just look for the ideal, just look for the sort of the optimal stopping place for that first layer of contractions. And it turns out that the optimum solution is right. What I'm going to call the recursive contraction algorithm. Which is contract to n over square root of 2. Oh, sorry, left out the loop. Repeat. Contract. So again, we're sort of getting bigger and bigger in our endpoint, in our stopping place. Where's the natural limit? The natural limit is when you're at n over a constant, right? It doesn't make sense to contract to less than a constant because you don't get a multiplicative improvement. So you should be contracting to a constant, and it actually turns out that the constant doesn't matter. So I'm going to contract to n over square root of 2 vertices, and then I'm going to recurse. The question is, how often should I repeat this? Well, if I contract to n over square root of 2 vertices, what is the probability of success? In other words, I still have a minimum cut to find. So here S is n over root 2, right? So what's the probability that I have not destroyed the minimum cut? Or that I have? Yes? It's a half, yes? So if I have a 50-50 chance of preserving the minimum cut, how often should I repeat this algorithm? Yeah?
2 times log n.
Yeah, if I wanted a high probability of success, I would do it log n times, but I'm going to settle for just a decent chance of success. Okay, so I'm just going to repeat twice. Okay, so this is actually now a very simple recursion, right? We start with our n vertices. We contract to n over root 2 vertices twice. Each of those is going to contract to n over 2 vertices twice, and so forth, until we get down to until we get down to a constant number of vertices and can check for the minimum cut directly. Okay? So, what is the runtime of this algorithm? And this is, by the way, is why I'm not going to repeat log n times. All right? I'll let you think for yourself about what would happen if I did 2 log n repetitions of shrinking to n over root 2 vertices. But if I shrink to only 2, right, my runtime is 2t of n over root 2 plus the n squared work of doing the contractions. Yes? Okay, if I just unroll this recurrence, right, this is going to be 4 times t of n over 2 plus 2 times order n over root 2 squared plus order n squared. Yes? But here I have an n over root 2 squared, which gives me a 2, and that cancels this 2, so this is just another order n squared, right? Same constant factors as here, right? So basically, each time I turn this crank, right? So now I have a 4, right? Before I had a 2 and a square root of 2. Now I have a 4 and a 2. You see this relationship will be preserved, that the outside will be the square of the inside, no matter how many times I turn the crank. And each time I turn the crank, I will spit out another order n squared. So after log n iterations, or log n turnings of the crank, this will be 2 to the log n, so I'll be down to a constant factor in size, and I will spit out log n squareds. So this is an order n squared log n runtime. Yes?
Is the probability of success OM log 1 over log n?
Well, we have to figure that out. That's the other piece, right? We have a runtime, but now we need to figure out a probability of success. So I did the runtime recurrence first because that is an entirely typical runtime recurrence that you've seen millions of them just like that before, and you all know how to solve them, and it's no big deal. Let's talk about the probability of success. Let's call this P of n. Okay. Can we write down a recurrence for the probability of success? So what determines success? Right? The algorithm succeeds if recursively one of the children succeeds. So how do we state that as a recurrence? Yes? Good. So you can go this route. You can actually imagine, like I have this very natural recursion tree with just 2 branches coming out of the recurrence, right? And you could treat each of them as sort of a potential success, right? So it's in a sense you could imagine that there's this sort of random tree of successes growing out of the root, right? I have the root, and it has maybe 0 successes, maybe 1 success, maybe 2 successes. Each of its successes now has 0 with probability a quarter, or 1 with probability a half, or 2 with probability a quarter of its own successes. So how about instead of calling these successes, I call them children? Okay, so you have a node, and it has a random number of children between 0 and 2 with a binomial distribution, right? And then each of those children has a child with distribution 0, 1, or 2, according to that binomial distribution, so on and so forth. Sorry, I was going to bring this up later, but since you proposed it, this is what is known as a branching process. And there is a whole beautiful theory of branching processes. When you're studying them in generality, you just say, what is the probability distribution? You specify an arbitrary probability distribution on the number of children that a node will have. And you make this the same for all nodes, for all generations of the population. And then you can ask really interesting questions, like the probability that your population dies out, or conversely, that it lives forever. Right? Also, somewhere in between, you can talk about the distribution and expectation of the number of generations. That survive. So you can go really far in this beautiful study of branching processes. And perhaps the very first important theorem that's proven for branching processes is that the sort of long-term effect is determined entirely by the expected number of children of your probability distribution. Okay. And it's determined in a very simple way. If it is less than 1, then everything dies out with probability 1, eventually. Okay. And this is pretty easy to see, actually. If the expected number of children is a constant factor less than 1 in the first generation, then the expected number of children in the second generation is the square of that constant factor. And it's the cube in the third generation, and so it's exponentially decreasing to 0. And you just use Markov's inequality to say that, eventually everything will die out. Okay. If it's greater than 1, then you live forever with constant probability. Kind of the same argument. There's a chance that the root has no children, and immediately everything dies out. But there's a constant probability that everything goes on forever. Okay. When it's equal to 1, this is known as the critical threshold. And here you die out with probability 1. But the expected number of generations is infinite, which feels a little bit paradoxical, but it just works out that way. Okay. So, which of these cases are we in for this recursion? What's the expected number of children of a node? Yeah? 1. Exactly. 2 children, each is successful with probability, or 2 potential children, each of which occurs with probability 1/2. So we have 1 expected child, so we're at the critical threshold. So our answer is complicated, right? It's not one or the other. Yes? Very interesting question. It's because of that running time recurrence. There's a tension here, right? If I contract a little bit less, okay, then that's good for the probability of success, but it's bad for the runtime. If I contract a little bit more, it's good for the runtime, but it's bad for the probability of success. And you will explore this a little bit in the problem set. Okay? And it turns out that the critical threshold is where you want to be. It makes things balance out properly. Okay. But because we're at the critical threshold, we don't have a trivial analysis of what goes on. We actually have to solve the recurrence. And there are some beautiful sledgehammers for solving the recurrence. Basically, if you're familiar with generating functions, in branching processes, you can get from the generating function of the number of children, there's a natural derivation from it for the generating function of the number of descendants. It's like a composition, right? You like the number of descendants at generation 2 is you iterate the generating function twice. The number of descendants at generation 3 is 3 iterations, and so forth. It's very beautiful. But we're going to do things the more basic way. Okay, so we have, but we still need to write out our recurrence now. And the way we're going to keep it more basic is by noticing that we don't really need to keep track of the exact number of successful descendants. We just need to know if there are any at all, right? So I don't care if it's 1 child or 1 successful child or 2 successful children. All that's really a problem is if there are no successful children, right? So if I'm writing this, so let's focus on that event, right? I want to know about the probability that I have, this is the probability I have at least 1 successful child, right? So how can I write that in terms of the success probability of the individual, of the children? Yes?
Well, it's like you can integrate the probability that you have no children. 1 minus that.
Exactly. So the probability that I have a successful child is 1 minus the probability that I have no successful children. Right? Now, what is the probability that I have no successful children? Well, that's the probability that both of my children are unsuccessful. Right? But those are independent events. So it's the child failure probability squared. Right? But the child failure probability is just 1 minus the child success probability. So I claim that this is a recurrence for the probability of success if you start with a graph of size n. Give you a chance to think about that and ask questions. Yes? Oh, thank you. I left off a term. Right, so my apologies. We need the successful recurrence, but we also have to do the right contractions first. Right? We need both of those things to happen in order for us to find the min cut at the end. Right? If we do bad contractions, our child might find a minimum cut of the graph that it gets, but it won't be the minimum cut of the original graph. Yes? Thank you. Gosh, I should look at my notes. I think we're okay now. Let's see. Yes, there it is. Okay. All right. So now to keep the notation from getting crazy, I'm just going to write P sub k for that's going to be my shorthand for P of P of root 2 to the kth power. So that I don't have to take so that I can be just doing a sort of indexes instead of powers. And that means I can write P sub k equals 1 minus a half of P sub k minus 1 all squared. Yes? We're just looking at everything in terms of powers of root 2. Okay. And if you expand this out, it's pk minus 1 minus 1/4 of pk minus 1 squared. So you probably have not seen a recurrence like this one before. Right? This is not your typical divide and conquer recurrence. For one thing, it's shrinking with k instead of growing. And there's also this weird quadratic term. Okay? So before solving it exactly, let me take you through a little back of the envelope estimate of what's going on, right? When I go from pk minus 1 to pk, I am subtracting 1/4 of pk. Like, if I'm currently at a value of pk minus 1, I then subtract this much of pk minus 1 in order to get to the next value. Yes? But if pk minus 1 is small, I'm not subtracting very much, right? Basically, I need to do this about 4 over pk minus 1 times before my current value shrinks by a constant factor, right? I'm shaving off. It's just like one of our amplification arguments, right? I'm shaving off this much each time. So after I do 4, if I do it 4 over pk minus 1 times, I'm going to be shaving off about 1 over e factor from the value, right? So essentially, pk is shrinking and shrinking, and the rate of shrinking is such that in order for it to divide by a constant factor, you have to go a number of steps equal to the inverse of the current value. Okay. So if I write qk as 1 over pk, what I'm saying is that I require about qk steps to double where this stands for multiplying by some constant, qk. Okay. Which is just saying that q sub 2k is about 2 times q sub k, which tells you that qk is linear in k. Which means that pk, we should expect pk to be about 1 over k. So that's just an example of how you might think about a weird recurrence. And once you think about it that way, you realize that you should rewrite your variables in terms of an inverse. So I'm going to write zk, and now I'm just going to show you what works, as 4 over pk minus 1, which means that pk is 4 over zk plus 1, which means that if you plug in zk into the pk recurrence, you discover that zk plus 1 is equal to zk plus 1 over zk. Okay. And that tells you that zk, right? Zk is increasing by a little bit more than 1 each time. So zk is certainly bigger than k. But since zk is bigger than k, it means that zk is only increasing by 1 plus 1 over k, right? And so zk is less than k plus the kth harmonic number. So zk is about k plus order, or log k. And now we go back and plug that in for pk, and we find out that pk is theta of 1 over k. But pk was p of square root of 2 to the k, so that tells us that p of n is theta of 1 over the natural log of n, or of 1 over log n. Yes? Yeah. Okay, so hopefully you followed the back of the envelope calculation and therefore believe the careful math, even if you weren't carefully checking every step. Yes? Any questions about what I've done here? Everybody sort of happy with the level of detail that we have here? Okay, so now we can summarize, right? We now have an algorithm, the recursive contraction algorithm. Its runtime is order n squared log n, and its probability of success is theta, or let me just say omega of 1 over log n. I shouldn't actually say theta. Theta is the recurrence is theta of 1 over log n, but I was making pessimistic assumptions about the success of the algorithm. So the algorithm might have a much bigger chance of success, but this is a lower bound on it. Okay. So now we're not too badly off, right? I mean, 1 over log n is pretty big. But it's still not, like, we still don't have an algorithm that runs with high probability, that succeeds with high probability. So what should we do? Yes, sorry, a question? Well, I can give you a graph where the probability of picking a min-cut edge is much larger than 1 over n squared. Sorry, of not picking it. Sorry, the probability of picking the probability of destroying your min-cut is much smaller than 1 over n squared. Yes? Log log n won't quite do. It would be nice, right? In order to handle a certain probability of success, you need to, yeah? Exactly. We run this algorithm log squared n times. Right? Log n times would give you a constant factor, and if you multiply that by log n, that constant factor exponentially decreases to a 1 over polynomial chance of failure. And so that gives us the min-cut with high probability in order n squared log cubed n time. And now we're not using any of the fancy complicated, like, it's funny, the fancy complicated flow algorithms were kind of a crutch for thinking about how to make this algorithm faster. But once you spiraled in deeply enough, they disappeared into the black hole and you were left with only contraction. Any questions? Let me show you another interesting thing. Our analysis of the contraction algorithm said, you know, there's this 1 over n squared chance of, at least a 1 over n squared chance of finding the minimum cut. There's a corollary here of this min-cut analysis. What is the largest number of min-cuts in a graph? Did I put this on your homework? I've forgotten. I didn't. Okay. So from what we know, can you give me a bound on the number of min-cuts that a graph can have? Right? Remember, I told you that there's a n choose 2 inverse probability that you will find the min-cut that we were looking at when we were analyzing the probability of success, right? So what does that tell us about the number of possible min-cuts? Yeah?
N cubed n over 2.
Why?
If
That's a very pessimistic bound. It's because that, I mean, that's talking about partitions, but it's not really saying anything about the structure of the graph, right? So this analysis up here, right, that we successfully find a min-cut, right? It was focused on a particular, right? We picked a certain min-cut and we said there's a 1 over n choose 2 chance that we find it, right? So let me ask you a kind of a crazy question. What is the expected number of min-cuts found? All right, let me put it a different way. Let's suppose that G has k min-cuts. What is the expected number found by the contraction algorithm? I mean, I told you up there that there's a 1 in n choose 2 chance of finding one, right? So what's the expected number that I find? Yeah?
The k out of the choose.
Exactly. It has to be, right? Each of them has a 1 over n choose 2 chance of being found. Okay, so that's the expected number I find. Now, if I contract 2 vertices, how many do I actually find? Yeah? I can only find 1, right? Right? This algorithm only finds 1 cut. So it must be the case that k over n choose 2 is at most 1, which tells us that k is at most n choose 2. You cannot have more than n choose 2 minimum cuts in an undirected graph. Okay. The more direct way to argue this is to say that if, like, the contraction algorithm gives you a probability distribution over cuts that are found, right? Each of the minimum cuts has a probability of 1 over n choose 2, and they don't share. So there can only be n choose 2 of them if you want that probability distribution to sum to 1. Yes? Okay. Is this tight? Yeah?
I think so because of, wait, it's true. Sorry.
Yeah? A cycle. Right? A cycle on n vertices has exactly n choose 2 min cuts. Because any 2 edges form a min cut. Okay. So this is not just constant factor tight, right? This simple analysis is exactly tight. And you can see that with the cycle, whatever cut you end up with is going to be, you can only contract to minimum cuts. There aren't any other 2-way cuts of the cycle. So it ends up completely tight. Okay. But now, let me go back to this recursive contraction algorithm, right? What we said about the recursive contraction algorithm is that it finds a min cut with high probability. Okay, but now we know there is only a polynomial number of minimum cuts. So what can we conclude? If each of those min cuts is found with high probability, but there's only a polynomial number of them, what can we say? Yes? Exactly. So our algorithm actually finds all min cuts with high probability, if you change the constants a little bit in how many times you iterate. Okay? And if you think about it, if you want to find all the min cuts, if you want to write them down, well, the cycle has n squared of them. So it's going to take you n squared time to list them all. And the recursive contraction algorithm runs in n squared log cubed n time. So it's almost optimal for enumerating all of the cuts. Okay, I think that's all I want to say about the recursive contraction algorithm for now. You're going to play with it a little bit more in your homework. It turns out that the things that I said here, they're about 2-way cuts. You can ask similar questions about dividing the graph into 3 pieces or 4 pieces, right? And this machinery all generalizes to finding 3-way cuts, 4-way cuts, and so on. So you can look for that in your homework. It also generalizes, and I will say more about this in lecture, to finding approximately minimum cuts. Okay? You want to find all the cuts that are within a factor of 2 of the minimum cut. Well, this machinery can be applied. I'll let you think a little bit about what you have to change if you're looking for a factor of 2. Okay? All right. So that's the story of the recursive contraction algorithm. It's not the end of the story for min cuts. After break, I will show you about how we can take a completely different approach that applies sampling to looking for min cuts. So grab a couple minutes, recover your energy, jump up and down, talk loudly.
What's the probability of that, given that we're expected to move into
Yeah. All right, so we're now going to change gears a little bit. I'm going to introduce you to a different algorithm for min cuts that uses a completely different approach than contraction. This is an algorithm due to Gabo. And actually, for utterly random reasons, I was actually a referee on this paper when he published it. So I got to see it early. So we're familiar with max flow and min cut, right? Or at least most of us are, right? It says that the value of the smallest cut is equal to the value of the maximum flow. And if I talk about that in terms of unweighted graphs, it says that the number of disjoint paths from S to T is equal to the size of the smallest cut separating S from T. And this is a directed graph concept, right? And Gabo's algorithm is actually a directed graph algorithm. But if you have a directed graph algorithm, you can always apply it to an undirected graph. So we have the max flow min cut theorem. which says that the number of ST paths is equal to the min ST cut. And this is sort of obvious in one direction, right? Because each path from S to T has to use up one of the edges of every cut. So there can't be more paths than there are edges in the smallest cut. It's much harder to prove in the opposite direction. And in advanced algorithms, we developed a bunch of machinery to demonstrate that this bound is tight. Yes? So now I'm going to ask whether we can make a similar one-way argument using a different structure, because now we're not interested in ST cuts. We're just interested in S cuts, right? We have a directed graph, and we want a cut with S on the inside and something on the outside. Right? So we're asking to find a minimum S cut, which has S on one side, and the value of the cut is going to be determined by the edges leaving the S side. Okay, so same directed notion of cut, but we're now not specifying a T. We're just saying something is on the other side. Okay, so the Maxwell min-cut theorem doesn't really seem to generalize, because if we want to send out a path from S, well, we don't know where to send it to, and if we pick the wrong T, we might stay on the inside and not use up one of the edges leaving the S cut. So the question is there something other than a path that would sort of guarantee that we use up at least one edge crossing the S cut? What set of edges would you need to take to be sure that you're taking at least one edge, leaving every set that contains S? Yeah? Yes, right? So an S arborescence is a tree of out edges rooted at S. So the directions matter, because this is a directed graph. And here we have a graph, or a tree, all of the edges flowing away from S. So this is kind of like a path to everywhere, right? As opposed to just a path to a specific T. All right? And it's easy to see that if you have an S arborescence, a spanning tree directed out from S, then one of its edges is going to have to cross every S cut. Yes? And so it turns out that there is a beautiful analogous duality theorem that says that the min S cut equals the maximum number of disjoint S arborescences in a graph. Yes?
The earlier thing, you said that the number of ST paths is equal to the min ST.
The number of disjoint ST paths. Okay. And same argument here. This is about finding disjoint span. And of course, I don't mean edge disjoint. I don't mean vertex disjoint. They're all on all the vertices, but these are edge disjoint arborescences. Okay? And this is not easy to prove. It uses matroid theory. It's a matroid intersection result, but it is true. Okay. And Gabo gave an algorithm for, when you talk about a disjoint set of things, it's called a packing. Okay? It's like when you pack your suitcase with disjoint pairs of socks, right? They're not allowed to overlap each other. They all have to fit in the suitcase. Okay? So Gabo gave a tree packing algorithm with a runtime of order m times c. Now, this should not look like a weird runtime because if you remember Maxflow, right? What's the most basic Maxflow algorithm? It's an augmenting path algorithm, right? You have a flow, and now you do a search, a depth first or breadth first search to find a path in the residual graph of the flow. And now you augment along that path, and that increases the flow by 1. Yes, and if we're talking about an unweighted graph, each of the paths that you find is going to be 1 unit of flow. And so the number of augmentations that you need to perform is going to be equal to the value of the flow. And so the runtime is going to be m times the value of the flow. Yes? Well, Gabo's algorithm is exactly the same, except that it uses augmenting trees. It says, okay, I've got a tree packing. This tree packing defines a residual graph in the obvious way. You reverse all the edges of the trees that you have. Now you find a new tree in this graph. It's not quite that simple, but you can take that new tree and add it to the tree packing that you have and have a one larger tree packing. And if you do this c times, then you will have packed the maximum possible number of trees. Yes? Sorry, c is the min cut value. This is the value that we're talking about, the min s cut. Okay? So I am not going to teach you this because it's entirely deterministic. But do you sort of buy the general description and methodology? So the point is that we have an augmenting tree algorithm, and therefore we can find min cuts in order MC time. Okay? Now, as I was saying, this is for directed graphs. Okay? But I claim I can use this to solve undirected min cut. How would I use this directed min cut algorithm to solve undirected min cut? I have an undirected graph, I want the min cut. I have an algorithm that works for directed graphs. So what should I do? I obviously need to make a directed graph. Right? What would be a good directed graph to make if I want to find the min cut of my undirected graph? Exactly. Right? So if I have an undirected graph, I can transform this into a bidirected version. I just take every undirected edge and I replace it with a pair of directed edges. Okay? So if you think about it, if I now take any cut, right, what were the undirected edges turn into these bidirected edges. So the value of if I call this S, if I put S over here, the value of the directed S cut, right, the number of edges going from left to right, is equal to the number of undirected edges I started with. It's also the value of the T cut. If I put a T over here, right, I also have the same number of directed edges going in the opposite direction, but those aren't counted for directed cuts. Directed cuts have a direction. So I can make this bidirected graph, and now I can look for S cuts. Which S should I use? Yeah, somebody's going, it doesn't matter, right? Take any vertex and call it S. right? It's going to be on this side or it's going to be on this side. Whichever side it's on, there's going to be a directed cut corresponding to the min cut going out from that vertex. Okay? So this just says that my directed min cut algorithm can be used to solve undirected min cut, and the runtime is the same. Everybody buy that? Okay, so now that's just a black box for us. But now is where we can start applying our ideas from randomization. Okay. We've been talking about sampling. Sampling is good for taking big things and making small things that give you insight into the big things. Right? We saw this with minimum spanning tree, where if we chose every edge with probability p, we got a tree that had where very few of the edges of the original graph were violating that minimum spanning that tree that we found, right? So it got us very close to the minimum spanning tree. Can we do something similar for flows, or for min cuts, right? Suppose that we construct G of P. What might we hope would happen to our cut problems? Well, let's start with something easy, right? So here we have a runtime of m times c, right? We'd be happy if m and c got smaller, right? So if we're using G of P, what happens to m? Yeah? Exactly, right? That's very straightforward. What might happen to c? Suppose we were very optimistic. What might we optimistically assume would happen to c? Well, we're starting with a graph that, there is a min cut, which has c edges crossing it, right? What happens when we sample? Yeah? We keep PC of these edges. So wouldn't it be nice if the minimum cut of the sampled graph ended up being around p times c? Because then we could run Gabo's algorithm in pm times pc, or p squared mc time. So it would get faster by a quadratic factor in p. Right? What do we have to worry about, though? Well, it's the same thing we always have to worry about with sampling, right? You get variance, right? Things deviate from their expectations, right? What is the deviation from expectation going to do if we use this approach, right? Suppose that all cuts deviate by a factor of 10% or something like that, right? From their expectations, right? What are the consequences going to be for our sampling algorithm? Yeah? Sorry, say again? So the runtime is what it is, right? Or sorry, if the runtime depends on the value of the min cut in the new graph. So let's start by asking that question, right? What can we say about the min cut in the new graph? Right? So suppose cuts only deviate by epsilon from their expectation when we do the sampling. Right? What can we say about what we're going to find when we look for a minimum cut in the sample? Yeah?
Well, that's fine. That means that each cut will be at most 1 plus epsilon times the value that you calculated, and the runtime will be, so C will be at most 1 plus epsilon times what you calculated.
Good. So what I might call C prime, the cut in the sampled graph, is going to be at most 1 plus epsilon times its expectation, right? And so that will tell us that the runtime is still going to be nice, right? But what can we say about the we find a min cut in this sampled graph, but does it tell us anything at all about the original graph? I mean, maybe some other, right? We've said here that the minimum cut of the original graph doesn't get too big, but maybe some other cut in the original graph got smaller under sampling than the min cut did, so we won't find the min cut. But can we say anything at all about what we find? Yeah? Exactly, right? The point is that any other cut, right, V, it's going to be more than 1 minus epsilon times its expectation, right? If I have this epsilon deviation, right? So if V is bigger than 1 plus epsilon over 1 minus epsilon times C, then V prime is going to be bigger than 1 plus epsilon times C, or C prime. So any cut that is bigger than 1 plus epsilon over 1 minus epsilon times the minimum cut is not going to be the minimum cut in the sample. Yes? So the min cut in the sample is a less than 1 plus epsilon over 1 minus epsilon, which is about 1 plus 2 epsilon, times minimum cut in the original. In other words, if all cuts stay within epsilon of their expectation, then finding the minimum cut in the sample gives us an approximately minimum cut in the original graph. Yes? So that's promising, right? Because we know that sampling keeps things near their expectations with high probability, right? I mean, we can just pull out the Chernoff bound, right? The probability that the min cut in G of P is outside 1 plus or minus epsilon times its expectation is at most e to the minus epsilon squared times that expectation over 3, right? That's our good old Chernoff bound. So if, this is around log n, right, we can say, hey, with high probability, the minimum cut is near its expectation. Okay? Are we done? Like, is everything great? We can just say, with high probability, all the min cuts are near their expectations, so we get an approximately minimum cut in the sample. Where's the sticking point? Why am I going to need a whole nother lecture in order to address this? What does with high probability mean? 1 over polynomial chance of failure, right? Is that enough? so that I can say that all of my cuts are near their expectation. Yes? Yes. And what's bad about that? What was that? Right. The problem is that there are 2 to the n minus 1 cuts. There are exponentially many cuts. So a high probability bound on like just 1 over a polynomial, if we just try and apply a union bound to that, that doesn't look very promising. It turns out that it works. I will show you on Friday. See you then. And you should check for a homework coming out tonight, of course. I noticed looking this over that I accidentally called problem set 7 problem set 6. I hope you all realize that it is in fact a different problem set that you should do, as opposed to one that you should skip because it's the same number as a previous problem set.